returns to almost the same place, we call that a year. Or take a pendulum. If you count how often the pendulum is, say, at one of the turning points, that gives you a measure of time. The reason this works is that once you have a theory for space-time, you can calculate that the thing you call time is related to the recurrences of certain events in a regular way. Then you measure the recurrence of these events to tell the passage of time. But then what do physicists mean if they say time is not real, as for example Lee Smolin has argued? As I have discussed in a series of earlier videos, we call something real in scientific terms if it is a necessary ingredient of a theory that correctly describes what we observe. Quarks, for example, are real not because we can see them, we cannot, but because they are necessary to correctly describe what particle physicists measure at the Large Hadron Collider. Time, for the same reason, is real because it's a necessary ingredient for Einstein's theory of general relativity to correctly describe observations. However, we know that general relativity is not fundamentally the correct theory. By this I mean that this theory has shortcomings that have so far not been resolved, notably singularities and the incompatibility with quantum theory. For this reason, most physicists, me included, think that general relativity is only an approximation to a better theory called quantum gravity. We don't yet have a theory of quantum gravity, but there is no shortage of speculations about what its properties may be. And one of the properties that it may have is that it does not have time. So this is what physicists mean when they say time is not real. They mean that time may not be an ingredient of the to-be-found theory of quantum gravity, or, if you're even more ambitious, a theory of everything. Time then exists only on an approximate emergent level. Personally, I find it misleading to say that in this case time is not real. It's like claiming that because our theories for the constituents of matter don't contain chairs, chairs are not real. That doesn't make any sense. But leaving aside that it's bad terminology, is it right that time might fundamentally not exist? I have to admit, it's not entirely implausible. That's because one of the major reasons why it's difficult to combine quantum theory with general relativity is that time is a dimension in general relativity. In quantum mechanics, on the other hand, time is not a dimension. It's not even something you can measure. It's not unobservable, as the physicists say. In fact, in quantum mechanics, it is entirely unclear how to answer a seemingly simple question like, what is the probability for the arrival time of a laser signal? Time is treated very differently in these two theories. What might a theory look like in which time is not real? One possibility is that our space-time might be embedded into just space, but it has a boundary where time turns to space. Note how carefully I have avoided saying before it turns to space. Before arguably is a meaningless word if you have no direction of time. It would be more accurate to say that what we usually call the early universe, where we expect a Big Bang, may actually have been outside of space-time, and there might have been only space, no time. Another possibility that physicists have discussed is that deep down the universe and everything in it is a network. What we usually call space-time is merely an approximation to the network in cases when the network is particularly regular. There are actually quite a few approaches that use this idea. The most recent one is Stephen Wolfram's hypergraphs. Finally, I should mention Julian Barber, who has argued that we don't need time to begin with. We do need it in general relativity, which is the currently accepted theory for the universe, but Barber has developed a theory that he claims is at least as good as general relativity and does not need time. Instead, it is a theory only about the relations between configurations of matter in space, which contain an order that we normally associate with the passage of time, but really the order in space by itself is already sufficient. Barber's view is certainly unconventional, and it may not lead anywhere, but then again, maybe he's onto something. He has just published a new book about his ideas. This video was sponsored by Brilliant, which is